We are Montgomery Blair High School from Silver Spring, Maryland, team 9479. I am Ishan Tawari, this is Annie Zhao, this is Jamie Vincent, this is Siddharth Taneja, and that is Andrew Kumo.
And over here on the judging panel, I'm Karen Bliss. I'm from Virginia Military Institute.
I'm Dan Connors from IBM Research.
Kelly Black, Math Department, University of Georgia.
Amanda Babson, National Park Service.
Chris Bergman, Leads Vestry Service.
You will have 15 minutes for your presentation. When there's 2 minutes remaining, I will give you a signal to let you know that we're almost done. After that, we'll have some questions for you for a few minutes, and then we'll be done.
Great. So hello judges and audience members. It is a true privilege to be here again. Today we will be sharing with you our recommendations to the National Park Service for the tides they are changing. Our overarching task was to look into the future of 5 coastal national parks: Kenai Fjords, Olympic, Padre Islands, Cape Hatteras, and Acadia. The first problem was twofold. We first forecasted how sea levels in each of the 5 parks will evolve into the forthcoming years, and then assessed the risk that those sea level changes pose to each park. In the second problem, we augmented our sea level models to account for natural disasters, ultimately determining how vulnerable each park is to the climate as a whole. In the final problem, we reconciled our climate vulnerability ratings with visitor statistics in order to advise the National Park Services on how to best allocate funds. We begin by delving into the tides of change. The first task entailed forecasting sea levels. Our initial thoughts were to simply perform a series of time-based regressions on the mean sea level data provided, but doing so posed the fundamental issue that we had no good mechanism of distinguishing between equally fitting models of the data. For instance, the linear and exponential models shown for Cape Hatteras. To remedy this, we developed a temperature-dependent sea level model. And to do so meaningfully, we have to impose a simplification that sea levels are directly contingent on temperature. This is a reasonable stipulation to make, as it is ultimately a rise in temperature that precipitates a melting of sea ice. To work within time constraints, we also have to run with the assumption that the effects of global temperatures overshadow those of local temperatures in driving local sea levels. Branching from our assumptions, we had to create a global temperature function to feed into each of our local sea level models. Due to the fact that temperature is contingent on a multitude of factors, we sought to create a polynomial approximation of the temperature function. To do so, we performed linear, quadratic, and cubic regressions on our temperature training set, comparing adjusted R-squared values to favor parsimonious models. We ultimately settled on a quadratic model after considering the high statistical significance of each involved variable and research in previous decades showing that the rate of sea level growth is steadily increasing. Equipped with the global temperature model, we then proceeded to construct 5 unique local sea level models for each park. Research has shown that historically, the rate of sea level change is directly contingent on temperature. However, this proportional relationship demands a steady discharge rate of ice, which is not held in previous years. To adjust, we have to introduce a velocity source, such that the rate of sea level change is contingent on both temperature and the rate at which temperature is changing. In doing so, we obtain a much more diverse family of solutions, which is more versatile and conformable to a much greater variety of data. We obtain the unique alpha and beta coefficients for each park through multivariate linear regression. An increase in the alpha coefficient corresponds to an increase in the rate of sea level change attributable to steady ice discharge, whereas an increase in the beta coefficient corresponds to an increase in the rate of sea level change attributable to the more short-term momentum of ice discharge. Here are scatter plots of the annual sea level changes in Acadia and Olympic, and below is a table of the regressed coefficients and the regressed standardized coefficients. It is interesting to note that how in Acadia, the short-term temperature factor completely dominates the steady temperature factor, whereas in Olympic, the opposite relationship holds true. Kenai Fjords and Cape Hatteras were our 2 most successful models, and in both of these models, there's a definite interplay between the steady and short-term temperature factors. It is of note that in Kenai Fjords, the short-term temperature factor is significantly negative, which, as we will see, produces a negatively sloping long-run sea level forecast. Unfortunately, our model for Padre Islands was quite dismal, with an R-squared of only 3%. One reason for this is the incredibly systematically high sea level variability in the waters engulfing the islands, which we see in the red in the map from Jet Propulsion Laboratories to the right. With our sea level differential model now developed, Annie will discuss the results and the risk implications.
Thank you, Ishan. Our model yields a graph of sea level height over time, which displays a universal positive trend. In particular, the similar upward trends of Acadia, Cape Hatteras, and Olympic are expected, since all 3 national parks lie along oceans. Meanwhile, Padre Islands and Kenai Fjords lie along gulfs, so the relationship between mean global temperature and sea level rise is complicated by the impact of local current patterns. To determine sea level risk ratings within the next 10, 20, and 50 years, we focus on the values in the table. By comparing these values to the topography of each of the national parks, we can qualitatively determine risk ratings. The elevation of Acadia National Park is well above our predicted sea level rise, rendering Acadia low risk. Similarly, Kenai Fjords greatly exceeds our predicted sea level rise. The same holds for Olympic National Park. Cape Hatteras is at low risk 10 and 20 years from now. However, by 2067, we expect a dramatic increase in sea level rise. Due to its easily eroded sedimentation, Cape Hatteras is at medium risk 50 years from now. The minority of Padre Islands is above 5 feet, so we categorize this national seashore as high risk at all 3 points in time. The sensitivity analysis of our model demonstrates our model sensitivity to the temperature coefficient alpha and a lack of sensitivity to the beta coefficient. Logically, T dependence represents a long-term trend in temperature growth, so we expect that a small variation in the T coefficient will have a significant impact on predicted sea level rise. The beta coefficient represents a short-term adjustment factor, so its effect is much less significant. To conclude problem 1, our model successfully makes a meaningful forecast within the next 5 decades, demonstrating that mean global temperature has an effect on sea levels and directly connecting to determining risk factors. However, we do not take into account the impact of local current patterns. Our model will not work in a 100-year timescale, as we do not account for the tipping point at which the Greenland and Antarctic ice sheets will melt and cause a dramatic increase in sea level rise. Jamie will now discuss problem 2.
Thank you, Annie. I will now discuss how these 5 national parks will fare over the next 50 years. In other words, is the coast clear? Our goal for problem 2 was to assign vulnerability indices to each of the 5 national parks based upon their susceptibility to climate-caused damage over the next 50 years. To simplify, we assume vulnerability is synonymous with monetary losses caused by hurricanes, wildfires, earthquakes, and general climate extremity. To quantify monetary losses, we created the following equation. The first term describes monetary losses due to natural disasters. For each natural disaster, the acreage affected was multiplied by the cost per acre. This was then summed over all 3 natural disasters and divided by the total acreage of the national park to get a per acre value. The second term describes monetary losses to an increase in general upkeep costs. Each park was assigned a climate extremity index, which was then normalized to an average of 1. Having an above average climate extremity caused above average general upkeep and a positive value for this second term, while having a below average climate extremity similarly causes a negative value for the second term. I will now discuss each of the natural disasters individually. Hurricanes cost $7.31 per acre, and every storm hits the entirety of the national park since they're so large. Tropical storms are assumed to cause 10% as much damage as hurricanes. Wildfires cost $225 per acre since they completely decimate the land they hit. Also, we were able to get accurate acreage affected data for each of the national parks. Padre Islands has predominantly brush fires, so these were assumed to be 1/10 as costly. Earthquakes cost $12 million on average, and since they are localized, it is assumed that they only hit 1 acre at a time. Also, only earthquakes above 5 on the modified Richter scale were considered important enough to be considered. Finally, the climate extremity index was given to us by NOAA. Having a high climate extremity causes things like precipitation, temperature, and foliage growth to be less predictable and thus causes an increase in general upkeep costs. As you can see on the map, Olympic and Kenai Fjords have low CEIs, while the other 3 parks have higher CEIs. Our results show that Cape Hatteras and Padre Islands are very vulnerable because they incur lots of damage from hurricanes and wildfires while also having high CEIs. Kenai Fjords and Olympic have low CEIs and do not incur lots of natural disaster damage, and thus they have low vulnerability. The strengths of this model are that it is entirely quantitative, and it gives concrete definition to the vague term of vulnerability. Also, it considers both general climate and the specific disasters on a discrete level. Some weaknesses include that it considers all hurricanes and earthquakes to be equal. Given more time, we would consider the obvious monetary differences between a Category 5 and a Category 3 hurricane. Finally, we are unsure how accurate using the regional CEI metric is, given the specific locality of each national park. Siddharth will now explain problem 3.
Thank you, Jamie. Now we'll discuss the third problem. The third problem, our primary goal was to advise the National Park Service on how to allocate funds to the 5 national parks. In order to do this, we needed to first predict visitation at each of the 5 national parks 50 years from now. In order to create our model, we made 2 major assumptions. First, we assumed that we can consider yearly statistics, as they still provide the trend and they also reduce our computational needs. Additionally, we assumed that all natural disasters would cause the same percentage decrease in visitation at each of the parks. Our general approach to doing this problem was to use a Monte Carlo simulation. Before we could run our simulation, however, we needed to first predict the visitation at each of the parks without accounting for natural disasters. We did this by simply running a quadratic regression on all of the past visitation data. As natural disasters are time localized, they will not affect this trend line, and the trend line will eliminate the variation due to them. In order to account for natural disasters, we combined all the effects of all the natural disasters into what we call a generic storm, which, whenever it would occur, would cause a 40% decrease in visitation, which would regress back towards the trend line. In order to calculate the cost of a generic storm, we summed the cost, affected acreage, and frequencies of all the disasters, and divided by the average acreage of the parks, which gives us the cost per acre of a generic storm. We did this to allow us to be able to account for the differences in how the effects of storms and the size of each of the 5 parks. Dividing the cost determined in Model 2 by the generic cost and then dividing by 52 gives us the expected number of generic storms in a week. As this number is less than 1, we impose a restriction that only 1 generic storm can occur in a week, we interpret this as a probability, which we use for our Monte Carlo simulation. Now Andrew will discuss our Monte Carlo results and conclude Model 3.
Thank you, Siddharth. Now, as Siddharth mentioned, we used a quadratic model. This is a change from our original paper where a linear model was used. We made this change for several reasons. First and foremost, evidently from these graphs, the quadratic model is a much stronger fit than a linear model. Second, a quadratic model produces much more sensible results. For example, the areas near Olympic are expected a large population increase in the next 50 years. A linear model predicts a decrease in population visitors, where the quadratic model predicts an increase in visitors. Padre Islands is not quite as strongly quadratic as the other 4. However, we chose to use a quadratic model for consistency with the other 4. These 2 graphs show the results from our simulation. The top one shows a single run, the bottom one shows 1,000 runs averaged together. As you can see from the top graph, there's a large amount of variation year to year due to the randomness of a Monte Carlo simulation. However, once 1,000 runs are averaged together, the variation significantly decreases, our model is much better. These are our predictions based solely on visitor statistics for how many visitors there will be in each park in the next 50 years. Now, the dots represent the actual predictions from the Monte Carlo simulation. As you can see, the Monte Carlo simulation, the generic storm probability, decrease our prediction from the general trend line. However, the difference is not significant on the scale. All parks except Padre Islands can expect somewhere between a 5 to 10-fold increase in visitors in the next 50 years, whereas Padre Islands should expect around a 30% decrease in the same time period. The major strengths of our model include that past visitor statistics we use to predict future visitor statistics, and that to account for the randomness associated with predicting natural disasters, a Monte Carlo simulation with inherent randomness was used. The 1,000 runs of our Monte Carlo simulation decreased variation in our predictions. The major weakness of our model was that it did not account for a lot of factors such as temperature predictions or economic growth predictions in certain areas. The mission of the National Park Service is to protect the natural environment for future generations to enjoy. As such, we recommend that a large amount of funding be allocated to parks such as Acadia, where visitorship will increase dramatically. However, funding should also be increased for parks devastated by the significant effects of climate change, such as Padre Islands and Cape Hatteras. We would like to thank our teachers, Mr. Rose and Mr. Stein, as well as our high school, Montgomery Blair magnet program. We'd also like to thank Moody's Mega Math Challenge and the Society for Industrial and Applied Mathematics program. Thank you.
In equation 4, and in your charts, there was a reference to a gamma constant, but you didn't mention it in your presentation. Can you explain what gamma is?
Sure. So gamma is more just an intercept, and as we only included first order and the rate, we included the temperature and the rate at which temperature is changing, there are definitely higher orders of that temperature change that we definitely did not account for. And we also had to run with the simplification that sea level growth is directly contingent on temperature, and there are certainly factors that we did not consider that drove sea level growth. And as a result, we intend gamma factor to sort of just encapsulate all of the factors that we did not consider in our sea level model.
So as I understand it, between the paper and the presentation, you changed the visitorship from a linear to a quadratic model. And as I followed, it seems like the order is still the same. Can you tell me a little bit about what changed in terms of your results between using very different models?
Sure. So basically what changed is that the order of magnitude of increase versus decrease changed. For example, Olympic, I believe, in our original paper had a slight decrease in visitorship. Whereas in our final model here, it predicted about a 6-fold increase in visitors.
Did you consider potential, what factors did you consider, given that the visitor data only covers about, it looks like 16, 17 years, and in the middle of that, there's also, 2008 to 2010 financial crisis that seems to correlate with some of the lower visitorship numbers?
We did not really consider factors such as economic measures.
You used regression to estimate the temperature in terms of time, and then you went back with your model for the local situation and used regression again to get the coefficients there. Why not just use regression in time for the local situation?
So to clarify your question, are you referring to using local temperature data as opposed to global temperature data?
Well, just to skip the temperature altogether and just use time.
Both use time. So as I sort of alluded to a little bit earlier, we wanted our model to have some semblance of a lot more meaning. And if we did it solely with respect to time, we would lump all sorts of variation just into some generic model which we really cannot interpret meaningfully. So in imposing the relationship of temperature, we sought to sort of create a more meaningful model which we could better interpret. And I think that we did so decently, given that we can interpret our alpha and beta coefficients with respect to how they affect the rate of sea level change.
On the big equation that has somehow in the denominator acres per park or average acreage per park, do you have?
Yes.
Yeah. It's not.
It's not.
Well, it's not. So the one I put on is slightly simplified just for ease of use. Basically what happened was here. So in the equation in the paper, there's 3 different terms for the different types of natural disasters. And so I just changed that to a summation here. And so that's why I went over how they're considered. So like for hurricanes, the acreage affected is always the total acreage of the national park, and then you just sum up the amount of hurricanes. And for earthquakes, since we have like a value of how much an earthquake causes damage, we assume that the earthquake only causes damage to the national park. And so that'll work in this equation if you just set acres affected to 1 for every single earthquake. And wildfires actually work exactly with this equation. And so I think the big number in the denominator for that's how big a hurricane is on average. So since we didn't use a cost per acre value in that, we were doing amount the hurricane hits times like the percentage of it hitting that is a national park. And now we're changing it to just saying that we have a cost per acre and then saying it just hits the entire national park.
Where did those cost per acre values come from for the various storms and
Just
fires?
researching on the internet, I think I have some semblance of charting where they come from, but
Do you think they were from urban areas or from rural areas like parks?
well, so wildfires are mainly rural areas because that's like I saw from the research statistics, it was mainly about like California wildfires in the actual forest, and like there's a lot of just work having to actually just put it out, which is a lot of what the cost actually is. It's just the man labor. It was hard to really do it for a hurricane. They did so much land, and the values were pretty low anyway per acre, so it wasn't that. That was the best number we could come up with. And earthquakes also, again, it was hard to tell. I didn't consider like the San Francisco earthquake that cost way more than $12 million, but I tried to consider that as best as I could.
Thank you.